Thanks everyone for coming. I'm going to get started. My name is Anton Lopyrev. I'm from Snapchat, and I'm going to be joined a little bit later by Youming and Ben from Snapchat as well. We work on a platform team, and today we're going to talk about attributed everything, or some of the strategies we use at Snap for ensuring quality, and those strategies are usually applicable for large apps. Cool. So first, I want to tell you a little bit of a really big project that we completed at Snap last year, where we wrote our Android app. I'm not going to spend much time in this talk talking about this project, but I am going to plug a session from last year that we did. It was called Building for the Future at Snap. Has anyone seen it? No? I see some snot people who've seen it. Cool. I highly recommend going and checking it out. I think it provides some really cool context for this talk, and it's also a really awesome session. One thing I will mention is that why did we rewrite the app? And the primary purpose of this was mostly to improve the performance and quality of our Android app. In fact, it was really central part of our marketing for the new app, as you can see in this really yellow slide. But one important thing you realize if you're trying to rewrite the app or any sort of big refactoring is that rewriting is just half of the effort. And one of the really important goals you should have if you're trying to do a big rewrite is how do you prevent things from regressing to where they used to be. So before we talk about that, what do we mean when we actually say app quality? I think it's generally a pretty overloaded term, but what it does come down to for Android apps is these three dimensions. It's bugs and crashes. We want our app to be stable. It's performance, we want our app to be really fast, and resource usage. And when we say resource usage, it's things like app size, disk usage, memory usage, and so on. And each one of these things could probably be its own talk, and we at Snap apply a lot of strategies to make sure the app is stable and performant, and there were a lot of talks at droidCon that talk about various strategies such as unit testing and automation testing. But for us, one of the really important things that is common across all of these verticals is attribution. And we believe attribution is key for quality as it provides guardrails for your company as it grows. And this is the central point of this talk. And a quick agenda, we're going to talk about what is attribution, why is it needed. We're going to talk about the attributed everything framework that we apply at Snap. And we're going to give two case studies for attribution. Youming is going to talk about frame drops, how we attribute performance related to UI performance. And Ben will jump in and talk about strategies we use for app size attribution. And we'll wrap up in the end to give you kind of a preview of what's coming next for us at Snap in terms of attribution. Cool. So what is attribution and why is this needed? I think one thing you quickly realize when you start software development is that crashes, bugs, and regressions will always happen. It's just the reality of engineering. We can't just snap our fingers and create a perfect app that will never crash, will never have bugs. The strategy that you usually apply is that you want to catch bugs and regressions sooner, and you want to make them much easier to triage, debug, and fix. And I highlighted triage here, given that as your team grows, triaging issues become exponentially harder. One interesting story I'd like to tell about this is that about 2 years ago when we decided to rewrite our Android app, I worked on a platform team, and about 35% of all crashes and all bugs were triaged to our team with a simple explanation on a ticket. I don't know who caused this bug, it's probably yours. And as you can imagine, it's not really scalable given that our team didn't really have 35% of all engineers at Snap. And this really highlights the problem that large companies run into is the tragedy of the commons. You really want to ensure that bugs and issues don't become hot potatoes. So how do we solve this at Snap? We try to think of our app as the operating system, where every major feature in the app is its own mini app with its own set of really important app metrics, such as crash rate, app size, frame rate, memory usage, disk usage, and so on. And maybe what's really interesting about our app, we don't really use activities. We have one activity with lots of different fragments. And in fact, it's just a collection of a lot of mini apps in one app. It's a video app, it's a chat app, it's a map app, and so on. So this view is really applicable for us. And this is where the attributed everything framework comes in. Attributed everything framework is partially a framework in a code, but partially a mental model where we want to make sure that we want to attribute every line of code, every piece of code, and every critical metric in the app to a specific team. So diving in a little more details, in the code, the attributed everything framework is composed out of two things. It's owners files and attributed features. So owners files are used for proactive or so-called compile time attribution for things like static code analysis, unit test coverage, lint rules, and app size attribution, which we'll talk about in one of the case studies. And attributed features are used for reactive or runtime attribution for things like crashes, resource usage, DB performance, and UI performance, which will also be one of the case studies. So let's dive in a little more details into each one of these. So owners files. Who out here uses some sort of owners files in your code base? CPY, just a couple of people. So an owners files is a really simple concept. Owners files is just a basic file in your code base that you drop in a directory, and it provides ownership for that code within that directory. And it's used for various purposes, from providing required reviewers for your code and so on. And there are a couple of known public implementation of owners files that you can actually go ahead and use right away. If you use GitHub, they have a code owners implementation. If you use Garrett, there's an owners plugin. For us, we use a slightly modified, our own version of owners file. And with one modification that you see here is that there's a Jira project. We use Jira, yay. Not a part of the stock. But what's really important for us when it comes down to owners files is that we want to attribute every line of code in our code base to a specific team. And we use it to understanding the code quality of each team. So what's important is that once we have these owners files, we can start building really interesting tools on top of these owners files. So one tool that we have in the code base, we call it the module browser. What we do is that we look at every Gradle module in a code, we track it down to an owners file, and then we aggregate it by Jira project, and then we analyze the code within that Jira project and those modules across a number of what we so-called code quality dimensions. It's things like unit test coverage, disabled unit tests, lint violations, and other penalties. And then what we try to do is provide a score from 0 to 100 for every module and in every Jira project. And we kind of track this over time, so you'll see changes from week over week. So why is this important outside of just being a pretty tool? Code quality is fundamentally subjective. It's really hard to come up with one thing that describes what makes good code. But what is important is that engineers are more likely to do the right thing when you provide them something that is easier to measure, track your progress over time, and compete with others. So what we've seen over the past 6 months after we added this tool is that with very limited mandate to go and fix things, we've seen the number of lint violations to reduce over time and code coverage increase over time. And this is an important representation how attribution can really help you with improving code quality and just the quality of your app. So the second part of the framework is the attributed features. And they are used for more reactively attributing crashes and metrics and runtime. And the actual attributed feature is actually composed out of 3 different concepts. And they're very simple. First one is Jira project. It's an additional enum that we have in a code base that represents all of Jira projects that we have in our code base. And from there on, attributed feature is just a simple data class with an additional string parameter. And then what it provides us is more kind of flexible, free-form attribution of the code in a code base. You could potentially extract this information from owners file if you had kind of like more fine-grained owners files in a code base. but we find this to be more flexible and more easy to maintain. And attributed feature is basically just some feature in the app. So in this case, let's say there's a stories attributed feature, which just represents the overall stories product. And attributed call side is a more fine-grained attribution within the feature that identifies just a place in the code. So in this case, you see we create a presenter call side within a stories feature. And what's cool about call sides, you can also chain them, so you can kind of drill down to a specific part in your code. So in this case, we create also a header call side from a presenter call side. So how do we use this? So one example is attributing Rx crashes. If you ever use Rx, you can sometimes end up with this really beautiful, very easy to understand stack trace. So once you have an attributed feature, we created an additional abstraction on top of Rx schedulers, what we call attributed Rx schedulers, that under the hood produce attributable runnables that then create attributed exceptions. And an attributed exception is just an exception that has an attributed call side attached to it. So in this case, we can create a set of Rx schedulers given a header call side, and then use it just like a normal set of Rx schedulers within our chain. So what's useful here is that if an exception happens, we know exactly what scheduler caused it. We can know which call side was used when this chain was created. We can also use it for things like CPU attribution. If we track how long does the each runnable run, et cetera, we can detect deadlocks and ANR attribution. So once we have this set of Rx schedulers, we can then end up with a much nicer exception that at least tells us where did this crash happen and what Jira project it can be triaged to automatically. So another usage of attributed features is for attributed navigation. At Snap, we have our own attributed navigation framework. It's not really important in too much detail for this talk what it does, but it's very similar to navhost, but we created it before navhost existed. But what's important here is that whenever we create a new page in the app, we have to use a feature to create it. And from here on, the benefits is that we can create navigation breadcrumbs that are useful for debugging. We can use last page crash attribution, and we can finally also attribute our frame drops. So I'll invite Youming over to talk about that.
Okay, hi everyone, this is Youming, and I'm also from App Platform team. And I'll be talking about how we attribute janky frames in Snapchat. Okay, so first of all, in Snapchat, we have a few problems to solve. We're a giant app with a lot of pages, a lot of user interactions. We want to understand where the janky user experience is, and we want to improve accordingly. The next goal is we want to track regressions and improvements over time. First of all, a little bit of background. So frame rate, or FPS, is used widely in the industry to attribute UI performance, but we think frame rate is actually for most of the Android application other than games. FPS is not actually a good metrics to measure that. Hopefully we can see that in this example. Let's see if you can tell which animation is smoother. I'll play one more time. So who do you think who thinks the right one is more smoother? Please raise your hand. Who think the left one is more smoother? Good, you all have a very good performance sense. So in this example, the left one is actually rendering only at 30 FPS, but the right one is at 52 frames per second. The reason for that is on the left side, all the frames are rendering just a bit over 16 milliseconds, which constantly dropping just one frame. But since it's rendering so stably and drops only one frame at each time, it doesn't distinguish it one frame from another. But on the right side, all the frames are rendering under 16 milliseconds, except for one frame that takes like 100 milliseconds to render. So that giant large frame drop distinguishes itself from the other frames, that gives the user impression that the animation is jankier. So now we know large frame job is a main contributor of janky experience. So how large is large? We also did some experiments very similar to the animation we did before. Basically, we just paused the UI thread for a small amount of time, and then let us feel whether we can feel this janky frame. And 80 milliseconds is the threshold we find that can separate the slow and the good experience. Above 80 milliseconds, it's very likely that user will feel this janky frame, but below that, it's not very easy to tell. And 700 milliseconds is another threshold we borrowed from Google. They have a frozen frame definition. If your app uses Android Vital dashboard, you probably have seen this number before. What does this mean is, if one frame takes over 700 milliseconds to render, it almost tells user that your app is janky and unusable on the device. So that's the frozen experience we want to check as well. Another condition we think that makes a janky experience is the user has to be interacting with the app. For example, scrolling, swiping, animation. This is in contrary to the case where user landed on a new page but stays there without doing anything. Even your UI thread is busy doing updates. Since user is not interacting with it, they probably will not notice there's a janky frame. That's why in Snapchat, we mainly just tracking page scroll and page transition in our app. Okay, now we get a definition. Let's see how we calculate that from the code. First of all, we need to get the frame duration. There are actually two ways. If your app is running on Android N and above, there's a very convenient API provided by Android called on-frame metrics available listener. That one will not only tells you how long each frame takes, but also tells you a bunch of breakdowns like how long does the measure and layout take, how long does the draw take, etc. So you can do really detailed breakdown if you want. But here we only care about the total duration. If your app is running below Android N, you have to tap into the choreographer's due frame callback. Basically, you just calculate the timestamp difference from this due frame and the previous due frame, and then get a frame duration. So for every frame we draw, we collect such data and increment it in a bad frame stats. We will increment that from app start until app is backgrounded. So the two stats we collect are mainly, one, the total bad frame milliseconds. That one will only accumulate if a frame is rendering above 80 milliseconds. Another stat we collect is an array called bad frame buckets. That one will basically split frames according to that duration into buckets so that you can understand what's the distribution of your frame rendering looks like. And in here, we'll also include bucket that's over 700 milliseconds, so we use that to determine whether there's a frozen frame or not. So after we have the frame stats, next is how we attribute the janky frame to attribute feature. As Anton mentioned before, we have an in-house navigation framework called DAC. That one is built alongside with attribute feature. So what that means is every page is associated with a name and a feature. So for example, when you navigate from camera to friends feed, you will know exactly when the navigation starts and when the navigation ends. And we can associate that with a feature or a theme. Here's one simple example. Let's say if you are swiping from camera to discover, when you start swiping, you will get a snapshot of the bad frame stats that we have been accumulating since app start. And we see that there's a total bad frame milliseconds equal to 100. That means before this event, we already have some bad frame occurred before. As we swiping, we continue accumulating the stats, and at the end, we see that the total bad frame milliseconds has been incremented to 196. Then we just simply calculate difference and then find out the bad frame milliseconds is over 80 milliseconds, which we can determine this is a slow event. In the case that if your frozen frame count has been incremented during swiping, you can also say that's a frozen event. So that's how we determine whether there's a frozen or slow event. Here's a summary of what we have been doing in the previous slides. First of all, we have a frame monitor that just get the frame duration from Android API. feed it to bad frame monitor that keeps incrementing the few stats we have talked about, like the bad frame, milliseconds, and then buckets. Next, say if you want to measure how smooth your scroll is, you can just have a scroll frame analytics class that whenever a scroll starts and ends, you call base bad frame analytics class and take a snapshot. Whenever it ends, you take another snapshot. And then basically you just calculate difference and then send it to event reporter and then report to backend. The good part of this is you can have as many as analytics class you want. For example, transition or whichever animation you want to measure without introduce much of overhead, because all the thing we're doing is just get a snapshot of the two stats we keep tracking and then calculate difference. So in that way, we can capture as many like interaction or pages as we want. For example, in here, we showed the major slow page transition percentage for all the major pages we have in Snapchat, and also the page scroll. In here, you can see like what the performance looks like compared to other features in your app. And the good part is that whenever there's a regression happen, you can quickly locate to which feature introduced it, and then which version. This also helps motivate developers to make improvements, because whatever optimization they do, it will be directly reflected in the dashboard as well. So that's for UI performance, and next I'll hand over to Ben, talk about app size.
Hey guys, I'm Ben Romano. I'm also on the platform team at Snapchat, and I work on build performance and app size reduction. So for attributing app size, it's kind of good to define what app size is. There's kind of two ways to look at this. So this can refer to the size on disk. So it's the APK expanded out and native libraries extracted out of the APK. And secondly, we can look at the download size. And so in this talk, we're going to use download size and app size interchangeably. So first off, why does download size matter? There was an article from Google back in 2017, which mentioned for every 6 megabyte increase in the APK size, there's actually 1% decrease in install conversion rate. So for a size like for an app like Snapchat, which is has a lot of features, we want to ensure that we're providing a rich feature set with like as little code as possible and keeping the app size down. So as part of that, there's a couple different aspects that we want to attribute for app size and a couple of kind of metrics we want to track over time. And so first off, we use app bundles at Snapchat, and we're looking into dynamic feature modules. So we want to be able to understand as we start kind of building out more and more feature modules, how big are these feature modules. Secondly, we also want to attribute across teams or Jira projects, and this can kind of give us a better insight on which specific teams are using up most of our app size. Maybe we can help talk to them and see other things we can do from the platform side to reduce the amount of code necessary to build out their features. Next, we want to attribute per file type. So this could be PNGs, WebP files, native libraries, and also DEX code. And lastly, as mentioned previously, we do use app bundles, and with app bundles, this allows us to ship kind of different sets of APKs depending on the user's device, and we want to understand with all these different configurations, what is the app size for that user. And additionally, not only do we want to look at these high-level metrics over time, we always want to also understand the app size per commit. So when someone makes a code change, someone introduces a PR, we want to understand, okay, how much of an app size change is there, and what contributed to that app size increase that we see from a PR. And lastly, we want to be able to do diffing across commits. So if we do see some regression which somehow slipped through our checks, we can understand which specific sections caused that and kind of fix our attribution and reporting. With that said, the first thing that we kind of want to look at is our app size dimensions. So with app bundles, we can do splitting on languages, We can split on the Android operating system. There's some different properties there. And also the ABI, so the architecture, whether it's 32-bit or 64-bit, and those all contribute heavily to like different app sizes per configurations. And lastly, we want to also understand the app size of our feature modules, which may be shipped to certain users or certain devices. And to enable that, we've kind of defined this data class, which is this app size dimensions. So it has all of these different kind of categories or dimensions that we're interested in. And we also attach some build metadata. So in this build metadata, we attach like our commit SHA, the branch, the PR number, and just kind of build variants as well. So anything to help us kind of slice and dice the data differently depending on like what we need to report on, whether it's from our master branches or release branches. So it gives us a lot of flexibility when we do want to kind of dive into like where our app size is coming from and how we're doing overall. And so as part of this, Google introduced this tool called Bundle Tool as part of the Android SDK for working with app bundles. It's a really cool tool, really easy to use. It's just a command line tool. And this tool is what's used behind the scenes to create a lot of the app bundles and the modules that go into it. And so as part of this, it's pretty straightforward actually to get the app size for all of these different configurations. So first off, after you've created an app bundle with Gradle, you can pass it into the CLI tool using this build APKs command, and it'll generate all of the different split APKs that are possible that could be shipped to your end users. And next, given this APKs file, this APK set file, you can pass it back into the bundle tool and run the get size total command. And as part of this, you can also pass in -- dimensions all, and this will give you a nice table of all of the different breakdowns for all the different dimensions, and you can kind of understand this is the app size increase if we're using English or Chinese or different screen densities and different ABIs. And so this gives us a pretty good insight on what the app size will be in the end for users. And secondly, as I mentioned, we're using feature modules, and we're starting to leverage that more. And unfortunately, the bundle tool still doesn't have kind of great support for this yet, but we would like to get app size attribution just on the specific module. And we've made a slight modification to it. We forked the tool, and we have some gist that you can look at to see the modification we made. It's relatively minor. And this now allows us to see the app size for a specific module or a set of modules. And as part of that, we can now kind of track our size over time for these modules. And it's kind of cool to see module size going up and then our base app going down, kind of shifting around where app size is. And the next thing we kind of want to look at is, okay, we have these high-level metrics that are interesting for us, but we also want to understand, okay, we saw this app size regression. What was the specific part of our code or specific file that's causing that? And so next, we kind of, per app bundle, we extract out an APK from it, and we look at the artifacts within the APK. So this can either be files like native libs, resources, or it can be Java code classes. And so for each artifact, as kind of Anton mentioned with the owner's file, every single piece of code in our app is attributed to a specific Jira project, and therefore, as when we're generating the artifacts from our APK, we can say, okay, this image is from the stories team or discover feed team, and we can tie that back to them and understand the app size by that. And lastly, so given an APK, we have this APK breakdown, which is the list of all artifacts, and again, some build metadata to associate it back to a specific commit SHA or PR, and just again for slicing and dicing data. And to enable this, we used APK Analyzer. So if you've ever dragged an APK into Android Studio, you've probably already seen this tool in action. It's really cool. I highly recommend checking this out. You get a lot of great insights by just dragging an APK into Android Studio. But additionally, it's also a CLI tool that you can just pass an APK in directly. And as part of that, we use this process to build out the app size per artifact given an APK. And so the process here is we've, again, kind of forked Google's tooling to extend it, kind of meet our demands. And so first off, we take our app bundle, extract out an APK. We next go through our Android repo, look through all of the files, all of the Java code, Kotlin code, and create this kind of owner's file mapping for every single file and class in our code base. And we pass both of these sets of data into the APK analyzer, and it'll generate us out some JSON report, which we can then publish up to BigQuery, and lastly, view it in Looker. Or if teams want to kind of analyze the data from BigQuery side, they can also just query that directly. And so as part of this, now that we have all of this reporting, we're able to easily track our app size over time. And as part of this, we can see what is our max byte count, our min byte count, some specific devices that we're really interested in, specifically the J2 Core and the Samsung S8 are popular devices. And as part of that, we can see, okay, we kind of have this, over time, new features get added and our app size increases slightly. But another interesting thing to note is that before app bundles, our max byte count was just our default byte count. All users received that, so now we're in a much better spot, and we can make kind of different decisions as far as how we do feature development at Snap. And lastly, I'd also like to note, in our max byte count, we see a dip just in the max byte count, and that's due to feature modules. So here, the different configurations can lead to different app sizes, so it does become a little more complex, and we want to have these breakdowns. And next, as part of our reporting, we have this APK breakdown, and we can see, okay, depending on the different artifact types, how much do they contribute to our app size. We can see that native libraries is a pretty big chunk of it, and with our reporting, every single artifact in our APK is attributed to a team, so we can drill down even further into this and see, oh, this specific native library is the problem. Let's reach out to them and see what we can do to optimize that, or this kind of chunk of our DEX code is really large. Let's see, can we make better ProGuard rules or other modifications to keep that size down? And so now that we have all this reporting, we have an easy way to understand our app size. We can now put that into our PR process. So on pre-merge, before you can merge code into our master and into our code base, we do some app size checking. And so on a change that is greater than 30 kilobytes, we block it, and then we ask the owner of that PR to kind of help investigate what's going wrong. And with our tooling, it should be easy to understand where that app size increase is coming from. And next, one thing we do on our iOS app, and we're starting to port over into Android as well, is we have this kind of concept of a quota system. As I mentioned earlier, we kind of see this, as time goes on, new features get added and our app size increases very small incrementally. And so we kind of have this death by 1,000 cuts. And with the quota system, we can allocate specific teams or Jira projects a set amount of app size, and that kind of prevents the slow bloat over time. Feature teams have to be a little more conscious about the features they're making, and maybe there's other things that we can maybe cut or refactor to be more optimal. And as part of this, teams can request more quota as they add new features to the app. Another thing I kind of want to talk about is how someone could identify app size opportunities. So one cool part of the Android build system is there is this thing called resource shrinking, and I highly recommend enabling it. It removes unused assets in the app. One kind of gotcha with this is that if you dynamically reference a resource, it might cause issues since this is static analysis. Another kind of caveat with this is it doesn't actually work with dynamic delivery yet and conditional delivery, so we can't actually enable it for the Snapchat app, unfortunately. And again, since we have this per file attribution to specific owners, we can see this unused asset is tied to a specific team and ask them to kind of fix that. And so to enable this process, there is this shrink resources flag in the build.gradle. Just enable that. It requires ProGuard also to be enabled, and it'll strip out your unused assets. As kind of mentioned before, we use dynamic feature modules, so we can't do this, but we still just kind of create this unused assets report, which will show feature teams these assets are unused, and we can remove it instead of just being automatically stripped out. And in this screenshot, we're just kind of showing, another extension to our module quality reports. We have another dimension that we kind of look at and expose the teams to help them understand their code quality. And with that said, with all of our attribution and all of our processes that we've put in place, our app size is at the lowest it's ever been. Where you're kind of starting from the top, we did our rewrite, massive app size reduction, enabled app bundles, reduced our app size again. And we kind of saw a slight bump with enabling 64-bit, but again, with app bundles, we're able to kind of mitigate that with different configurations. And now it's kind of have a pretty good understanding of where app size is coming, and it's easier for us to optimize over time. With that said, there's still some remaining challenges. A lot of our attribution processes occur within a single repo, and so when we consume artifacts from other repos, for example, native libraries or ARs, those don't have like owners files associated with them, so we just kind of assign one team to it, but it would be better to kind of get a better breakdown of those since multiple teams might be contributing to those external artifacts. Next, it's also kind of interesting to look at attributing update size. Unfortunately, the tooling from Google isn't not very easy to understand this right now, and with feature modules, this can also kind of change the impact of the update size, the deltas there. And lastly, with like increased usage of app bundles, it kind of really expands the number of configurations we have. And as mentioned earlier, we forked bundle tool. It still doesn't have the full set of analytics that we'd want to get from it. And lastly, it's just kind of an overall topic of like, how do we make the appropriate trade-off? We know that a feature team's app size is X amount, but are we making the right trade-offs here? And just kind of general discussions around that. And with that, I'll hand it back off to Anton for closing remarks.
Cool. Thank you, Ben and Youming. So I'll wrap this up. So I think hopefully these two kind of case studies give you a good example of how do we use attribution and how you could use attribution. But for us, it's been a really essential key to making sure we keep the quality of the app after our rewrite. And it helps us to keep the app size, test coverage, crash rate in check. And there are many benefits of unified attribution, but in particular, given that we know exactly which team is causing issues, we spend a lot less time triaging bugs and crashes. And even though they do happen, we can at least fix them faster than they occur. And with the attribution also provides us a more unified set of metrics for each team that we can also have automated alerting on those metrics and a standard playbook for investigating those regressions. And if there's one thing you can take away from this talk is that if you don't have any concept of attribution in your code base today, whether it's owners files or something on top of that, I highly recommend adding it, given that as your team grows, it becomes a lot harder to attribute your code. And if you invest into this early, it will pay dividends in the long run. For Snap, this work doesn't stop here. We have a lot more work to do. And in particular, some metrics are actually really hard to attribute. And two reasons for that are largely complexity and lack of good tooling from Android side. And two types of metrics are memory and battery. When it comes to memory, there are different types of memory out there with their own unique challenges, such as code memory, native memory, and graphics memory. We kind of today focus on attributing some specific things, such as bitmaps, and we're starting to attribute code memory to specific teams by looking at our dagger graph and kind of analyzing it statically and mapping it to owners files. For battery, it's actually really hard to accurately measure battery, and it also attributed in production. But what we do is that we focus on attributing some related metrics, such as background network activity, so we can understand which teams are making network calls, and we can attribute also the wake-ups of the radio. So with that, I think we'll move on to questions, and we also have a booth on the second floor, so if you guys don't want to ask a question in public, you can come and hang out. Thank you.